Hello again, everyone. So in our last lectures, we've been talking about functions and then trigonometric functions, sines and cosines and whatnot. And so now we want to put those ideas together and think about inverse functions. So remember, a function was a rule that would take an x that's standing there minding its own business, not doing anybody any harm, but it would transform it into another number. We'll call that f of x. So we have, notation so that we can describe what happens to this poor x as he got turned into f of x. Well, we could try doing that backwards, right? What if the f of x wants to go back to being x? Then that's what an inverse function does. So in other words, an inverse function is another function, right? And it will take and undo what f did. So if you look at the odd looking formula with all the multicolors there in the middle of the screen, x, right, sitting right in the middle, first has f done to it, then f inverse done to it, and lo and behold, on the right side of the equal sign, it's back to just being x again. And the same thing the other way around. You could do f inverse, then you could do f, and again, x goes back to being what it was to start with. So f and f inverse undo each other. So you've probably seen this before with trig functions, or maybe with exponential and log functions. This is a really common idea. Functions are things that change numbers into other numbers, and inverse functions undo it. Now, the notation is a little bit confusing sometimes here, because notice that what we use for a function, say f, is just f, but we write the inverse function as f with a little -1 superscript, right? And there's a little bit of danger here, okay? Because we use the little -1 subscript to mean something else in math, right? When you see, say, x with a little -1, that really means 1 over x. That's not what we mean here when we write the little -1 as kind of an exponent almost. It's not really an exponent, it's part of the notation for a function. See, the reason we write x with a -1 to mean 1 over x is because that's how, it works out nicely with the exponent rules. But with functions, the idea was, well, it's the same sort of thing. It's the inverse, right? It's kind of like the one that undoes the other when we multiply. So we're just sort of stuck with this notation. It's not perfect, but because it can cause some confusion, right? Because f with the little -1 is not the same as 1 over f. So this needs an example. So let's think about nice, easy functions. So f of x is 2x plus 1. Nice equation of a line, super easy. So what does this function f do? So x was minding its own business, along came f, doubled it, and added 1 to it. If I want to undo that process, I'll subtract 1 and divide by 2. That's what f inverse has to do. And that's very much not the same as like dividing by the f, right? Because think about 7. If I plug 7 into f, it gets doubled and 1 added to it, so that turns out to be 15. So 1 over f is 1 over 15. But f inverse of 7 isn't 1 over 15, right? Let's think about this. What number will get turned into 7? It's 3, because 2 times 3 plus 1 gives you 7. In other words, f inverse of 7 should be 3, right? Not 1 over 15. So again, it's a little bit irritating because we use the same notation to mean two different things. So just be warned that when you see f with a little -1, it's not an exponent, it's an inverse function marker, right? Okay, well, one problem can show up if you try to figure out how to compute an inverse, because look at a function that's like x squared. Right? So the problem is f of 2 is 4, right? Because you take 2, you square it, you get 4. But the same thing happens to -2. It gets squared, 2 times 2, and turned into 4. So if we try to go backwards from 4, should we go back to the 2 or should we go back to the -2? Oh, crud, that's a problem, right? I don't know which one I should go back to, right? This function doesn't have an inverse because remember, a function should match up a number with only one answer, and there's two answers for this. So not every function is going to have an inverse. Right? Only a function where there's an obvious choice of what to go back to. So a function is one-to-one if there is an obvious choice of what to go back to. In other words, being more precise here, if f of one number equals f of another number, then those two numbers were really the same to start with. In other words, you couldn't have had the situation we had on the last slide, where you had two different numbers that both gave you 4 as the value of the function. Right? So what that means is, if you have a one-to-one function, there's an obvious x to go with every y. So that's why we call it one-to-one. One x goes with one y goes with one x. It all matches up nicely. And there's a way to see this from the graph. Because if we look at the graph of x squared, there's a problem. So remember, we use the vertical line test to determine if something's a function. But if I drew a horizontal line, right? So I matched up the graph with one particular y, then notice it'll hit the graph twice. So for this value of y, there are two values of x's that go with it. That's a problem. So that means this function doesn't have an inverse. On the other hand, if I had a graph of something like x cubed, sure enough, if I draw horizontal lines across this graph, then every y is only going to match up with one x. So something else we can do while we're playing with graphs, we can look at the graph of an original function, so say x cubed that we have here, and graph its inverse. And there's a cute trick for doing this, because what's happening when we do the inverse is x and y's are sort of switching roles, right? Instead of x being the input that gives us a y, the inverse function will take a y and give us an x. So if x and y are kind of switching roles, then what we do is we draw a line, y equals x, and we switch the x's and y's. In other words, we can sort of reflect this graph so that x's turn into y. So I'm going to draw part of this graph here. Notice that this part I've drawn is below the line I've drawn on the solid reflection line. So the inverse should flip across that, right? So instead of this little part of the graph that I've drawn below the line, I'm going to draw it above the line, right? And then the next part of the graph that is above the line and shooting off toward infinity, this next part will be below the line and kind of, again, shoot off toward infinity, but not as steeply. Same thing happens on the other side. So this next sort of bubble there is above the line, so it ends up being below the line. And then this last part that's below the line here, right? Well, it ends up being above the line, shooting off that way. Okay? So my hand-drawn sketch is not perfect, of course. So I'm going to replace what I have and show you what it would look like if I had the computer draw it. So we get a nice, prettier graph. It's much more precise. But you can see that all that happens when we go from a one-to-one function to its inverse is we've just flipped the graph around that 45-degree, really shouldn't say degrees, pi over 4 radian line that went through the origin. Well, so here's an example with a little algebra. Right? If I give you a function like 2x cubed plus 5, that turns out to be one-to-one. If you don't believe it, you can graph it and then check the horizontal line test. So it will have an inverse function. So how do we find the inverse? Right? How do we go through and do the algebra to come up with the inverse function? And the answer is, well, we just do the algebra to turn y's back into x's, or another way to say that is to solve this equation so that instead of plugging in x's and getting y's, we plug in y's and get out an x. In other words, let's solve this for the x that it came from. So what do? I need to subtract 5 from both sides and then divide by 2. That'll get the x by itself. And then take the cube root, and that gets the x completely solved by itself. Again, the idea was y was the number that came from an x. So if I want to undo it, I've got to solve back for x. And if you think about this, makes sense, right? We've cubed we've multiplied by 2, we've added 5. So the opposite set of operations would be subtracting by 5, dividing by 2, and then cube rooting. Now, one thing that can be a little confusing sometimes about this is we usually want to write our functions. You'll notice that this function said find f inverse of x, not f inverse of y. So we really want to have a formula with x's in it. So if I'm going to write f inverse of x, I'm using x, well, to mean two different things here. X was getting plugged into f of x. Now if I want to write this where x is getting plugged into f inverse of x, I'll switch the roles of x and y here so that my formula is written with x's. Just because we like to write the formulas with x's, and that's the only reason for switching the variables. Okay, so I mentioned we've done some really cool things with functions and with trigonometric functions. So if you look at a graph of, say, sine of x here, well, remember that sine is a wave, right? Its graph is definitely not one-to-one. If you draw a horizontal line through that, it's going to hit that graph infinitely many times as the wave goes up and down. So can't find an inverse function as it is. But if we erased part of the graph, right, then we would have just a piece that if we drew horizontal lines through that, then we would have a one-to-one function. So for each of our trig functions, we'll have to cut back the domain so that we have just a part of the graph, and that part of the graph there will be one-to-one. Now, here's something really important to keep in mind. The trig functions took an angle and gave us back a number, right? Like we would have sine of some angle, pi over 4 or pi over 6 or something like that. And it would give us a number. That number would be the opposite over the hypotenuse. It'd be a fraction, right? So trig functions take an angle, give us back a number. What about an inverse trig function? Well, that undoes that process. So it takes the number and gives us back an angle, which again is why that cutting down the domain is so important. Because remember, you can take an angle and add 2 pi to it and get the same angle again, right? So you have to know exactly what angle it is you're wanting to get out of this. Here's an example with some numbers. Inverse cosine of square root of 3 over 2. Well, okay, so this is an angle that we're going to recognize. Because if I draw out, say, a triangle that would have this square root of 3 as its adjacent side and 2 as its hypotenuse, we recognize that triangle. That's one of our friends, right? This is a square root of 3 and a 2, and the missing side we realize is 1. This is our friend, the 1, 2, square root of 3 triangle, and because the short side, the 1, is on the opposite side, we get kind of this long, skinny triangle, which means this guy is pi over 6 for the angle. So inverse cosine of square root of 3 over 2 is pi over 6. Now, you might remember from the earlier video where we talked about trig functions that if we were looking for a triangle who has an adjacent side of square root of 3 and an hypotenuse of 2, there's actually 2 triangles we could draw. We could draw this one in the first quadrant, or we could flip this triangle upside down and draw one in the fourth quadrant where the opposite side switched from 1 to -1, but we don't need that to find the cosine. So there's actually another angle we could have picked here. So how did I know to pick this one? The answer is, for our purposes, because we're going to cut down the domain of cosine, we're only going to get answers from inverse cosine that are in the first quadrant or the second. We'll do something similar with sine and tangent. We'll only get answers from inverse sine and inverse tangent that are in the first quadrant or the fourth quadrant. And that's what we mean about having to cut down the domains because of the original sine and cosine in order to have just one answer come out. All right, well, this is one of my favorite problems, partly because this shows up again in Calculus 2, but this is a really, really cool question. So if you look closely at this, it takes a little thinking to understand what in the world that mess of tangents and inverse cosines and stuff means. But let's start with the x over 4. So x over 4, that's a number. It's getting inverse cosigned, which means it's going to take that number, x over 4, Inverse cosine will turn that back into an angle. Great. Everything in red there is an angle. Then the blue tangent will take that angle and give us back a number. Right? So this is really cool. We can just draw this picture and read off the answer. In other words, I start with the red inverse cosine of x over 4. So what angle would that be? Well, it'd be an angle that has, because cosine is adjacent over hypotenuse, x for its adjacent side, 4 for its hypotenuse. Okay, great. So then I can just read off the tangent, except, well, I'm missing a side. So what's the missing side? Well, we get that from the Pythagorean theorem because it's a right triangle. So I'm missing the adjacent side. So I know that x squared plus the adjacent side squared would be 4 squared, or 16. So I just solve for this. So I would get 4 squared minus x squared, and then take the square root to get us that missing opposite side. And now I have the red angle, right, drawn there with its labeled with all the different sides of the triangle. So I can just read off the tangent. So I've gone from x over 4, that was a number, to inverse cosine of x over 4, that's an angle. And now I read off the tangent of that angle to go back to a number. The tangent is going to be the opposite over the adjacent, so square root of 16 minus x squared over x. So here's one more really, really cool example. This is sine of 2 inverse tangent of x over 3. So again, let's look really carefully at what we have here. The 3 over x. The 3 over x is a number. Inverse tangent of that is an angle. Then that angle is going to get doubled. Oh wow, I made the angle bigger. And then that angle is going to have its sine taken, so I'll go back and get some sort of a fraction. Okay, well, I can't just draw a triangle to make this work because of that doubling of the angle. I draw a picture of the angle for inverse tangent, then how do I know how to double it, right? That doesn't work exactly. But we have those trig identities we've learned, and we do have a trig identity for sine of twice an angle. Sine of 2 theta is 2 sine of theta times cosine of theta. So, in this problem, sine of 2 inverse tangent of x over 3, that's just an angle, is 2 inverse tangent of 3 over x cosine of inverse tangent of 3 over x. So I've used this trig identity to now get rid of the problem of having to double the angle. I'm not doubling the angle anymore. I'm doing it with this trig identity. So I can draw the triangle that comes from an angle with a tangent of 3 over x. That would give me an opposite side of 3 and an adjacent side of x. Right? So now I have drawn that inverse tangent angle. Of course, I'm missing a side, so I'll have to figure that out. But once I have that, I can read off sine and cosine for that angle. Now, this is easy because it's the hypotenuse that I'm missing. So the Pythagorean theorem says I should get adjacent side squared plus hypotenuse side squared. Sorry, I said that completely backwards. Adjacent side squared plus the opposite side squared should give me the hypotenuse squared. So the hypotenuse would be the square root of 3 squared plus x squared. Now that I've labeled all the sides of the triangle, I can just read off now the sine and the cosine. So my final answer will be 2 from the trig identity. Sine of this angle, which would be 3 over the square root of 9 plus x squared, times the cosine of this angle, which would be the adjacent side x over the hypotenuse square root of 9 plus x squared. And if I really wanted to simplify that, which is not strictly necessary, but I could multiply those fractions together. The 2 square roots would cancel. The 2 and the 3 multiply together to give me a 6. So I end up with a pretty simple, easy answer.